Hello, everybody. Today we are doing a lesson on permutations of objects where they may not be ordered, or maybe in other words, permutations where some of the objects are identical. Because up to this point, every time we've arranged a group of objects, so people or cards, um, they've been different. They've been distinct. So we need to develop tools to handle that. So here we go. A little bit of a motivation question. At this point, you guys should be able to figure out how many ways you can arrange the word bark because there are 4 distinct letters. But how would your answer change if 2 of the letters repeated, like in barb, or 3, like in the word lull? So if you want to pause the video lesson here and actually try working those out on your own, that'd be great. And you can unpause when you're ready. I'm going to go through those now. So for bark, using our current knowledge, there's 4 distinct letters. We're arranging all of them. 4 factorial is 24. For barb, there won't be 24 distinct ones because, for example, if I labeled the B's B1 and B2, well, I'd get the same word if I switch those guys around. So for all of the 24 arrangements I had before, there's going to be 2 that are identical where I just switch the order of the B's. So for barb, we're going to have half of the available arrangements, so 12. And then we'll talk more about lull in a second. But for lull, imagine 3 different L's. And any different way I arrange those 3 L's is going to give me the same word, lull. And if you think about how many ways can you arrange 3 objects, that's 3 factorial, right? So for lull, you'd have your original 24, but there are 3 factorial equals 3 factorial ways to, just gonna bring up my eraser tool here, get rid of that little, looks like a decimal. 3 factorial ways, or 6 ways to arrange those L's. And so you'd actually only have 4 ways to arrange letters in lull, which makes sense because you can have lull, or the U could be first, or the U could be third, or the U could be last. You can see why it's 4. But we just talked a little bit about the reasoning. This kind of motivates a rule for arranging objects where some of them are identical. So again, looking more at lull specifically. Wanted to pop, let's just squeeze that U in there. Yeah, so if you label the L's individually, there's 6 different ways that you can arrange those L's so that it gives the same word. So L1 then U, and then switch the L2 and L3 order, or you can have L1 and L3 at the end, and you can switch their order around. Or you could have L3 in the front and L1 and L2 on the end and just change their order around. But you can see they all spell lull. And there was 6 arrangements for, like, in their positions for L1, L2, and L3. Of course, with our knowledge, we know that comes from 3 factorial ways to arrange those objects. So this motivates a rule that we can now use to determine the number of arrangements in a group of n objects when you have, so let's say you have a certain amount of elements that are identical and you have A of them, and then you have B identical elements of some other kind, and then C of some other kind, and so on and so forth, is this. So the number of arrangements is n factorial But as we've seen, that can give repeats if some of the letters, or in previous case letters or objects, repeat. So you divide by how many times the first object repeats times how many times the second object repeats. And if there's a third group of objects that are the same, times factorial. And then just do that as much as you need to for as many repeating elements. Let's put that into practice, and then it should really sink home. So we're going to find the number of arrangements in 3 different letters or 3 different words. Or my kids are into Yo Gabba Gabba, so just chose that, for example. So how many ways can we arrange DJ Lance Rock? So look at the number of letters. 5, 6, there are 11 letters. So 11 factorial. And then we scan through and we look for letters that repeats. So I can see that there's 2 C's. And I believe that's the only things that repeat. So this is just 11 factorial. Don't know why I made such a big fraction there. It's actually just 11 factorial. Change back to my pen. Over 2 factorial. That's it. 11 factorial over 2 factorial. Only the C's are repeating, and there's 2 of them. So you divide by 2 factorial, and then you can work that out. In this case, that's something that's fairly easy to punch into our calculators. That is 19,958,400 ways to arrange letters in DJ Lance Rock. If we look at B, Broby is a character in Yo Gabba Gabba. How many ways can we arrange his name? So there are 6 letters in Broby, but this time we have 2 letters repeating. We have 2 B's and 2 E's. So for each repeating element, we have to divide by how many times they repeat. So there are 2 B's, divide by 2 factorial. There are 2 E's, divide by another 2 factorial. And now we can work it out. Now you may choose to do this in multiple steps. You may choose to do it in 1 step. If you'd like to do multiple steps, I might recommend doing the top first. So 6 factorial is 720. 2 factorial is 2. 2 factorial is 2. Multiply those. Your calculator can handle multiplications pretty easily. Strings of factorials, I should say. But when you start dividing and multiplying, your calculator might lead you astray. So maybe you want to do it in a couple steps. But that does give you 180 ways. So why don't you try C? How many letters are there? What are the repeating ones? Just got to be careful. If you want to pause it, try it on your own, you can. But here we go. So Yo Gabba Gabba has 12 letters. So 12 factorial. The Y's don't repeat, nor do O's, but we do have 2 G's, so 2 factorial. We have 4 A's, so divide by 4 factorial for the A's, and 4 B's. Divide by 4 factorial for the B's. And from here, you can work it out. You can do it in 1 step on your calculator, which I'm going to do in this case. Or you can do it in 2 steps, whatever you need to do. But in the end, we should all come to 415,800. All right, so we've applied our new rule for when there are repeating elements. What we're going to do next is just play around with this idea in various scenarios and see how it can be useful. And it's really interesting how useful this concept can be. You can solve a wide variety of problems using it. Let's continue. So here, Barbara is hanging a display of clothing imprinted with the school logo. She has 5 sweatshirts, 3 t-shirts, and 4 pairs of sweatpants. And the implication here is those are all identical. How many ways can she line up the display? So we have, let's use, what would be a good letter to use for sweatshirts? So I'll just use S for sweatshirts. So we have 5 of them. S, 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 S. Call those sweatshirts. For t-shirts, I'll use maybe a T. So we have 3 t-shirts. And then maybe I'll use P for sweatpants. We have 4 pairs. P, 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 P. So this question really boils down to like how many ways can you arrange the letters with like 5 S's, 3 T's, and 4 P's. So it's very similar to the previous 3 we did. And we know now how to do that. They are just double checking. There are 12 objects, 5 repeating sweaters, 3 repeating t-shirts, and 4 repeating pairs of sweatpants. For this particular one, I might show a bit more work. Again, if you're comfortable going right to your answer, that's really good. But some of you guys, at least initially, might want a little bit more guidance on punching these in. So again, do the top as one thing. A string of multiplications, especially factorials, your calculator can handle. It can do 3 factorial times, or 5 times factorial times 3 factorial times 4 factorial really easily. Nothing there to mess you up. 17,280. And then you can divide those numbers. But again, if you're comfortable doing that in one step, then go for it. So 27,720. All right, very good. So we're just applying this idea to real life question. Why don't you try the next one? So a hockey team in their, I guess it's a 24-game season, had 12 wins, 8 losses, and 4 ties. You know, they could have won 12 and then lost 8 and then tied 4, or won a couple, lost 1, tied 1, and there could be a whole lot of different mixtures of wins, losses, and ties that gave them that record. How many orders could these outcomes have happened? Well, I'll wait a moment while you guys, or you can pause and you guys can try this, or you can unpause and follow along with me. So here we go. You'll hopefully you noticed that, or added these up and got 24 games in total. So an expression for the number of orders this could have happened. We're going to start with 24 factorial. There are 12 wins, so we'll have to divide by 12 factorial. 8 losses, 8 factorial, and divided by 4 ties, or 4 factorial for the ties. Now, in this particular calculation, 24 factorial is too big to display on your calculator screen. So you may just want to do this all at once, everything stored in your calculator. It is still going to be a pretty big number. But the final result should fit still on your standard calculator screen. It is over over a billion different ways their season could have played out, which is pretty interesting. 1,338,555,220 different orders. So we went right to the calculation. You know, in this question, probably a little bit impractical to write out 12 W's. Yeah, I've already gotten tired of that. So we just went right to the calculation. All right, let's continue. In this question, we've got the word numbers, and we're going to figure out how many ways we can order those letters if we need to keep the consonants in their proper order. So there could be obviously this question might seem not very useful in real life, practically speaking, but there are many applications where this could be useful. If we wanted to insert certain objects in a certain spot, but keep other objects in order. So what does it mean that the consonants are in their proper order? So for example, possible orders would be like, N, M, they have to be in proper order. Well, that's fine. It didn't say alphabetical order. Proper order is fine. So just they got to keep their order that they normally are in. So N has to be first, then M, then the next consonant is B, and then R and S. They have to be in that order. So one possible arrangement would be like this with the U and E at the end, or N, U, M, E, and then B, R, S. But basically, or you could have the U and the E first, and then N, M, B, R, S. But it always has to be N first, then M, then B, then R, then S. So this actually it's a straightforward question, but like the solution is not so straightforward. And it might not be obvious how to go about it. I'll show you though. What we're going to do is we're going to treat the consonants, the things that we are trying to fix into a proper order, we're going to treat them as identical. So doing that means what we're really doing is we're going to be rearranging the letters in the word or series of letters C, U, C, C, E, C, C. So we've replaced all the letters or all the consonants just with the C. We're going to treat them as identical. Because now maybe you can see, now we're just kind of concerned about like, okay, well, where can we stick the E's? You know, how many different spots, like U and the E at the end or in the middle, or it kind of makes it easy to visualize what's going on here. And we actually know how to arrange these letters. We've done a lot of examples already. That's just 5 factorial, or excuse me, there's 7 letters, 7 factorial. And there's 5 repeating consonants. So 7 factorial divided by 5 factorial. You can give that a go. That's just equal to 42. So there's 42 different arrangements like that, where the N, M, B, R, S are in that order, and the U and the E are sprinkled in. And the way to do it is to treat the things that need to be in a proper order, treat them as identical. The key idea here, in problems like this, when you want to keep things in a fixed order, a general rule is, you divide by that factorial. So if you look at the previous question, we had 5 consonants, right? Oh, I think that has an O. So we divided by 5 factorial. So 7 letters in total, 5 are consonants, divided by 5 factorial. That rule works all the time. Why don't you guys try applying that rule to a similar question? Here we're going to arrange the letters in explain. And the vowels have to be in alphabetical order. So for example, you have to have A, then E, then I, and then the letters can come in any order. So like X, N, P, L, something like that would work. Or A, X, E, L, P, and I. That would work too, because it's A, then E, then I. So give it a try. You can pause it, unpause it when you're ready, or follow along now. So explain has 7 letters in it, and we are keeping the vowels in alphabetical order, and there's 3 vowels, so we'll just divide by 3 factorial. 7 factorial over 3 factorial. That's it. And that's 840 different permutations. So we can quickly and efficiently do problems like this that on the surface seem complex using our new knowledge today as well. So a pretty powerful tool. We have one more application of our new knowledge, and that's pathway problems. So in this question, we're going to figure out how many ways that a person could go from point A to point B on that grid, assuming that they're just kind of going directly, going up and right, and never like going backwards or left. Because then you'd have infinitely many options if they just like went round and round and round. But they have to go up, they have to go right. How many ways from A to B? This might be a useful problem for a city planner where the streets are all laid out in grids. Let's see, how can we do this problem? The key is the following. If you think about it, every combination of going from A to B involves going up twice and right twice. So whether that's up, right, or right, up, right, or right, up, they all get you from A to B. They all have 2 ups and two rights. You can think of that as like 4 letters. Maybe you would think of it this way: we have to have 2 ups and 2 rights. And so the question is, how many ways can we arrange those 2 ups and 2 rights? And now we know how to do that, right? It's 4 factorial over 2 factorial. The u's repeat twice. 2 factorial. The r's repeat twice. And that just gives you 6. There's 6 ways. Now that one was probably not too hard to count. You could probably have just counted up the 6 ways. But for larger grids, that would be impractical. Can you guys apply the same strategy to the next one, which is a 3x3 Lake City grid? How many ways could you go from point A to point B on this one? So you can pause the video and unpause when you're ready, or do it along with me here. In this question, from A to B, that would involve going up 3 times and right 3 times. So the number of ways that we can go up 3 times and right 3 times, or arranged ups and rights, is 6 factorial, 6 total movements. 3 factorial for the u's, another 3 factorial for the r's. And we just have to work that out. And works out to about 20 different arrangements for there, 20 different possible pathways from A to B. So it's kind of neat how many situations this skill can be applied to. We've done rearranging letters to start off, to problems where we have to keep things in a certain order, to pathway problems which seemingly were disconnected from organized counting. So yeah, lots of neat examples. I've provided a lot of practice for you guys to try, and I will start when I can. I've got a link to a site that has video solutions to most of the questions that you are working through. So guys, make sure you are keeping up with things. Trying to check in and do some work every day. Good luck with the practice. See you guys online, and have a great day.